Hello everyone, welcome to the last lecture of this humidity and chemical sensors module where we were discussing the gas sensors part. We have discussed various transduction technique to detect these gases in trace level. Today we are going to discuss a special kind of gas sensor which is based on field effect transistors. Usually you might have read about FETs, particularly for switch applications and other transistor kind of application in particularly ICs. Okay, all of we know that these FETs has evolved from JFETs. So MOSFETs have characteristic very similar to JFETs and some additional characteristic which makes them useful for not only for switching applications but also for other applications. Okay, so there are basically two type of MOSFETs, depletion type and enhancement type. Mostly the sensors that we are going to discuss today are based on enhancement type field effect transistors. So before we actually go into discussion of this FET type of gas sensors, let us quickly see what is a field effect transistor and how the drain current can be modulated. Okay, so metal oxide semiconductor field effect transistor, in short form we call it MOSFET or sometime even FET, is widely used for implementing integrated circuits, right? As a consequence, we have seen that the chips have more than 10 power 6, 10 power 8 kind of transistor in a small area. Okay, that is quite possible because of the small size of the transistors. Okay, so if you see operation of an channel enhancement type FET, the construction of this FET is something like this. You have a source, a drain, gate oxide. This is your gate oxide. Then you have a gate. This gate is usually made up of polycrystalline silicon or sometime some metals, right, like gold, platinum, palladium. Even cheaper FETs have aluminum also as the gate material. Then usually if you see, this is a 3-terminal device, but sometime if you consider the effect of the substrate, you have another terminal called as body. Okay, so sometime it is also considered as a 4-terminal device. Okay, for this course we are considering it as a 3-terminal device itself. Okay, so the major part of this FET is its source, drain, substrate, gate and gate oxide, right? So source and drain, if you see this is, as I have mentioned, is a n-channel enhancement type MOSFET. So the body or the substrate is a p-type material, say p-type silicon. Okay, the body is a p-type silicon. In this two areas, this area and this area has been heavily doped. This doping is achieved either by ion implantation or by diffusion. Okay, so two areas has been doped heavily with n-type impurities. Okay, so these diffused regions are known as source and drain. Okay, the substrate is a lightly doped p-type silicon. Okay, then you have a gate, a metal layer placed over a thin insulating layer of silicon dioxide. Mostly this is SiO2. Okay, the thickness is around 10 to 50 angstrom for this gate oxide, which separate it from the substrate. Even if this channel length is much larger than 100 nanometer or so, so say if the channel is even a micron long, okay, then also the gate oxide is not above 100 angstrom thick. Okay, so the gate oxide is usually very thin. Okay, so the gate oxide is covered by a conducting material. Mostly this is polycrystalline silicon or sometime metal, right? Now if you see, there is no channel formed here. Okay, and that's why we call it a enhancement type MOSFET. Okay, we have to create certain conditions to create this channel. Okay, so to get the drain current, first we have to create a channel for the electron to flow. Okay, to create a channel, we have to apply a voltage between the gate and the source terminal, right? So you have to apply some voltage between source and the gate terminal. I am calling it a voltage VGS. All right. Please note that in this condition, the voltage at the gate is higher. Now, if I am applying a higher potential at this gate voltage, say a positive potential at this gate terminal, what will happen? This is a p-type substrate where the majority is coming from movement of majority of the carrier is holes, right? And you have electron as minority carrier. True? Now, when you have applied a positive potential at this gate, what will happen is this minority carrier electron, which is of course there in this substrate, will get attracted towards this gate. Since gate oxide is very thin, the effect of this is there on this channel, right? Of course, this acts as a dielectric. So this oxide, this region acts as a dielectric. So what it is doing here is it is not allowing this electron, to reach to the gate terminal. Okay, so it is coming in between this channel or in this substrate and the gate. So it can come to this point, but it cannot cross this barrier layer. So this dielectric material is helping in accumulating this electron near this junction. Okay, here if you see, there are two junctions. One is semiconductor. This p-type substrate is, this area is semiconductor, and then you have an oxide. Okay, so this junction is semiconductor, insulator junction, right? And this area is a insulator, conductor junction, right? So you have two different junctions over here. Now, at semiconductor insulator junction, this electron is going to populate or it is going to accumulate. Okay, because of this dielectric layer, this is not going to the gate terminal. Okay, when you keep on increasing this gate voltage with respect to source, what is happening is lot of electrons accumulate here and it constitute a path. So nearly all the holes in this region have been moved to the bulk of this substrate, right? So you can consider two different cases, or you can consider this from two different angles. If you are applying a very high positive voltage here, what you are doing is you are actually attracting electron towards this junction. Okay, but at the same time what you are doing is this positive charge will repel the holes in this area. Okay, so this area near to this junction will be deprived of any holes. So the whole of this area is now populated with electrons. Holes are pushed away from this terminal, which is actually increasing the n-type behavior at this terminal. Okay. Now, if you go on increasing this, a time will come when a n channel is created between these two wells. Okay. So, you have sufficient number of electron to form a channel. Okay. So, the VGS voltage at which the channel is created is called the threshold voltage, VT. Okay. So, we can conclude from this discussion that when VGS is greater than threshold voltage, a n channel is formed at the gate terminal. Okay. So, to form a channel at the gate terminal, we have to achieve a condition where VGS is greater than threshold voltage. Okay. Now, you have a channel voltage, but still there is no current, right? You have a channel, but you also want a current to flow through this channel. Okay. So, applying a voltage between the drain and source keeps the drain at a higher potential. Okay. If you keep this drain at some higher potential as compared to this source, okay, this is lower, this is higher, okay, you can induce a current in this channel. Okay. This voltage at drain is known as VDS. Okay. On applying this voltage, current will start flowing from drain to source. Okay. This current is known as ID current. Okay. Drain current. Okay. So, when VGS is greater than VT and VDS is greater than 0, the current ID flow from this drain to source, right? Now, this condition cannot be like, if it suggests that if I keep on increasing this VDS, ID will keep on increasing, but that is not the truth. Okay. In practical, what happened that when you increase this drain terminal voltage, a reverse bias is formed at the PN junction near the drain terminal. Okay. Because of this PN junction formation, there is a thick depletion region formed. Okay. Because this is under a reverse bias condition. Okay. So, on increasing this VDS further, the channel near the drain terminal becomes narrow. So, now earlier the channel was like this, now the channel has become like this. Okay. The drain current will face more resistance near the drain terminal. Okay. Now, a situation will reach when the drain current becomes constant and will not increase further. Okay. So, even you are increasing the drain voltage, okay, the current is not increasing. Okay. This situation is called the pinch off situation, and the drain current is called the saturation current. Okay. The voltage at which we will get saturation current is known as saturation voltage. So, this is the basic operation of this FETs. Okay. And usually we have seen that these FETs are used for transistor application or other amplifier kind of application. But today what we are going to do is we are going to use these FETs for sensing applications. Okay. And they are very popular because they are very accurate. Okay. And they can also be easily integrated with the current CMOS fabrication technology. Okay. That's why these FET type of devices are very popular, particularly for sensing applications. So, we will see this FETs, how they can be used for the sensing application, particularly in the context of gas sensors. Okay. There are other things in this FETs like its characteristic and all, which is beyond the scope of this course. You can study about those characteristics in other courses, particularly in the course of analog circuits as well as in the various fabrication technology courses. Okay. So, there are various type of FET type gas sensors. For example, a simple thin film transistor, okay, catalytic metal gate field effect transistors, Then there are other variations like suspended gate FETs, then capacitily coupled FETs, horizontally floating gate FETs, okay, and so on. Okay, you have a number of FET modifications available for the sensing application. So these are some of them, but this list contain only few of them, but the list is even much larger. For example, there is a gate all around field effect transistor, which is very popular in sensing application, particularly categorized under catalytic metal gate field effect transistors. All right. So let's discuss some of these transistors for sensing applications. Let's consider the case of thin film transistor or TFTs. Okay, so TFTs, as we know, is a 3-terminal device, and this is a basic construction of a TFT for sensing application. So this is your source, this is the gate, this is the insulating layer, the oxide layer that I was talking about, and this is the gate. Okay, and this is this pink layer is showing the sensing layer. Okay, this is the sensing layer. Okay, if you see this structure, this is a bottom gated device. Okay, just now which device I was discussing in this FET was a top gated device. Okay, but this thin film transistor that I am discussing now is a bottom gated structure. Okay, so the gate is not at the top but at the bottom. Okay, this utilize a sensing layer as its active layer. Okay, so the sensing layer, which is actually the channel, okay, is the active layer. So the FET that we have discussed some time back was not having any channel initially, right? But this kind of device has channel initially, and these are this comes under the thin film transistor. Okay, the active layer is exposed to the air, so the toxic gases can interact at this sensing layer itself. Okay, so the device structure is very simple. The sensing layer is exposed and gate is present at the backside. Okay, the detection through direct interaction between active layer and gas molecules is possible. Okay, so this interaction will alter the current flowing in this sensing layer or the ID current. All right, sensing current flowing through this sensing material or this sensing channel is the major source of information for this sensing application. So say initially the current was ID when, say, this sensing layer is some metal oxide, for example. Okay, say this is a metal oxide. When gas molecules interact with the sensing layer, okay, the current will now be something, say, ID dash. Okay, therefore I can say that the current has been altered, and if I can, find this difference and calibrate this device against some standard device, I can even find the concentration of the gas analyte. Okay, further I can modify the structure of the sensing layer to make it selective towards certain gases. Okay, similarly you can understand this for other structures also. Okay, now there is another configuration which is catalytic metal gate field effect transistor. Okay, just have a look on the device structure. This is a top gated structure. You have a catalytic metal gate, okay, insulating layer and the substrate layer, and source and drain are present at its places. This pink layer here also shows the, if you see here, there is no channel. Okay, and this catalytic metal gate itself interact with the toxic gases. So now in the previous case what you have seen is the gas molecule were interacting with the sensing layer directly and gate was at the backside. Okay, but here what is happening is this gas molecules is not interacting with the channel, but it is directly interacting with the gate metal itself. Okay, so the sensing receptor here is the gate metal. Okay, so here what people has done is they have utilized this catalytic and porous metal as its gate. Okay, please note that this kind of devices are very popular to detect those gases which has some affinity towards particular catalyst. Okay, say for example, hydrogen gas. Okay, hydrogen gas has very much affinity towards platinum and palladium based materials. So for those kind of gases, this kind of structure is very popular. Okay, so what it does, it detects the dipole layer formed at the interface between the metal gate and the gate insulator by some catalytic reaction. Okay, so usually this kind of structure is not suitable for large VOC molecules, but it is suitable for small gas molecules, because the gas molecule has to penetrate through this catalytic metal gate. Okay, usually this gate metal is made up of some porous materials. Okay, so as I have mentioned that this type of device is very popular for hydrogen gas detection. Okay, then there is another class of device which is suspended gate field effect transistor. Have a look at the structure of the suspended gate field effect transistor. You have a gate terminal. This is the sensing layer. This is the insulator, and this is as usual the source and drain fabricated over a substrate. Okay, if you see, there is a small air gap between the sensing layer and the insulator. Of course, the gate is present on top of the sensing layer. Okay, since it looks like the gate is suspended, so that its name comes from that, suspended gate, SGFET, suspended gate field effect transistor. Okay, if you see, there is an air gap formed between the sensing layer and in the field effect transistor. Okay, so the gas molecules is flowing through this air gap. Okay, so the gas I want to sense is introduced in this layer. If you introduce the gas layer in this, what it will do is, it will have affinity, or it will have the ability to interact with the sensing layer. Okay, reactions of the gas molecule and the sensing layer happens, and a potential difference is generated, or even there is some alteration in the drain current. Okay, the effect of this reaction is calculated in terms of the modulation of this drain current as well as the change in the gate potential. Okay, the sensitivity and response speed of this kind of structure is very much dependent on this air gap. Okay, so it will have different sensitivity and response time and recovery time if the air gap is x, and it will have different when the distance increases or decreases by a distance delta x. Okay, now there is another class of device which is capacitively coupled field effect transistor. So just have a look on the structure of this device. This also have a suspended gate which is covering the sensing layer. So this is your sensing layer, and gate is made like a step kind of structure. Okay, and rest insulator, source and drain and substrate remain similar. Okay, here also there is a air gap. Okay, and gas can come in this area, in this air gap. Okay, now if you see, the gate is also in contact with the insulator in this device structure. Okay, so the gas molecule is flowing through this gap, and the reaction of gas molecules and sensing layer again happens to generate some kind of potential difference. But at the same time, this gas molecule can also see the gate metal. Okay, so the sensitivity and response speed decreases in this kind of device when the air gap between this sensing layer and the insulator decreases. Okay, then you have other structures where something like horizontal floating gate field effect transistor, we call it HFG FETs. Okay, here you have a control gate and floating gate facing each other in a horizontal direction. So you have this control gate, this is your control gate. Okay, so two gate structure, this is your floating gate. Okay, and they faces each other in a horizontal direction, and the sensing layer is covering both the area, the control gate as well as the floating gate. Okay, gas molecules flowing through this air gap. Okay, reaction of the gas molecules and the sensing layer. Of course, the gas molecules is interacting with the sensing layer here. Okay, the reaction of the gas molecules and the sensing layer happens to create a potential difference at the floating gate. Okay, and this control gate acts as a reference. Okay, so high coupling ratio due to the two gates facing each other in an interdigitated form, and this kind of structure, although looks complicated, is simpler process as compared to the SG FET and the other FET that you have seen. So these HFG FETs are, although looks in construction little complicated, but their operation is simpler as compared to SG FETs and CC FET. Particularly if you see this air gap that were created in CC FET as well as this SG FET, okay, this makes it more complicated. If you see, the air gap in case of SG FET is very simple. Okay, there is no hanging kind of structure. Okay, you can make it narrower or wider by making this CG and FG close to each other, because they are facing each other horizontally. Okay, so the fabrication, although it looks very difficult, is easier as compared to the other two structures that we have seen. Okay, fine. So we have seen a number of field effect transistors for sensing application. Okay, and we have now some background on detection of these gases. Okay, if I summarize the concept of this humidity and chemical sensor, okay, there is a concept of receptor and transducer for this kind of devices. Receptor is something which sees the gas molecules directly, okay, or which interact with the gas molecules, and the transducer is something which converts that interaction into some electrical energy. Of course, then you have electrical circuit on top of that, okay, and you gather the response by data acquisition system and the other things. Okay, mostly these transducers are fabricated by various lithography techniques, as we have discussed this field effect transistor based transducers, or capacitive transducers, or SAW transducers, or even simple resistive transducers. All have very interdigitated kind of structure or other precision areas which can only be patterned by some lithography techniques. Okay, so various lithography techniques are utilized to fabricate those things. Okay, nowadays in the modern electronic era, there are various maskless technologies, particularly for flexible substrates like printing device. Different printing techniques are available. You can pattern the transducer directly on a flexible substrates. Okay, receptor materials, that the sensing material that I am calling since the first lecture in this module, are mostly metal oxides like zinc oxide, tin oxide, like that. Okay, and in the modern era, people have started using graphene and some other materials like two-dimensional transition metal dichalcogenides like tungsten sulfide, moly sulfide, and so on. Okay, and then people have also started exploring beyond 2D materials like metal oxide frameworks and others. Okay, similarly, this receptor film fabrication on the surface of transducer is very crucial, and usually there are various physical and chemical techniques to deposit these films. Okay, in a simple laboratory condition, if you are making this sensing material by some chemical process in lab, you can test it by simple drop casting. But if you want to commercialize this device, or if you are seeing any practical devices, they are deposited by some physical vapor deposition techniques like sputtering, thermal evaporation, like that. Okay, but in practical, in laboratory, you can also use a simple spin coating kind of structure. Okay, and then of course we are also talking about massless deposition. So various printing technologies are available to print these materials on a transducer substrate. Okay, I hope that the concept of detection of humidity and gases are clear to you. Okay, we'll meet in the next module, which is sixth module, where we will discuss different ways to monitor temperature, okay, which is a physical parameter and very crucial in industry process as well as for day-to-day life. Thank you.